Don't be alarmed by the fact that it says part 2. You don't have to have read or seen part 1 to understand it. We did blog about it. There's a post on the SOASTA blog, and the slides are on SlideShare somewhere. But really what this talk is about is, as Steve said, we started this project about a year ago and really started doing the analysis, because just managing the data and dealing with that is a huge undertaking. If anybody's ever tried to manage a lot of data, they'll understand and appreciate how hard that can be. We kind of crunched it and did a lot of validation on it, and came to Velocity in Santa Clara with a handful of what we thought were interesting findings, some of them controversial. And then we started, we had questions about some of the findings ourselves. This is a process, and it's kind of a never-ending process. So Pat did the heavy lifting on going back into the data and filtering it some more. And we're going to talk about kind of how we got from before there to here. Does that pretty much sum it up?
Yeah, I think that's pretty good.
Okay.
Oh, and woohoo, mic works.
Oh, yeah.
Wasn't entirely sure about that.
Okay. So if you have any questions, you can tweet at us. We'll tweet back. And yeah, we'll let you take over.
So I'll just get this out of the way really quickly. So machine learning, as far as it goes for RUM, it's very much a case of using a sledgehammer to crack a nut. Every time I've talked to any one of the people on the brain team or anyone at Google who really does machine learning for a living, they laugh at me when I tell them sort of, okay, yeah, we have 93 different inputs we're looking at, and they're like, run that on your phone. It's totally, and I'll be the first to admit, I am not the best with analytics in general. I am not a statistician. Someone who is, and someone who's a real data scientist, could probably find non-machine learning ways to do a lot of the stuff that I'm doing here. I'm a code monkey, so I like throwing machines at the problem, and I let the machines figure everything out for me. So first off, everything we're going to be talking about here is all open source. There's not a whole lot of code, just to get that out of the way. So machine learning, for whatever reason, is all in Python. I guess everyone in the machine learning community, all of the libraries and everything else are all based around Python. And when I say all of the code, the real work in most of the machine learning is in preparing the data to get it into a way that you can do the training. With all the machine learning libraries we have these days, the actual code for doing the machine learning is like 10 lines of code. So yeah, I've got 10 lines of code up on GitHub. Woohoo! So just really quick basics and a little background just so you sort of know where we're coming at. With the machine learning, there's a whole bunch of different things. We're largely looking at two aspects of it. There's the deep learning, which for the most part, neural nets, that kind of a thing. It's basically you take all of the inputs on the left, the little circle dots, and they're using machines. They're trying to copy what the brain does with synapses, basically, and neurons. And they basically go, okay, we have these inputs, we connect them to everyone else, and then we take all of those and connect them to all of the others until we have an output at the end. And those connections in between, we're just going to guess like crazy and keep guessing until we find something that gives us the answer that we want. And that's all machine learning really is. It's brute force the crap out of it until you find out what those relationships are that happen to give you the answer you want in the end. And so that's why it's like embarrassingly parallel. It runs really well on GPUs and that kind of stuff because those work really well on parallel problems. Throw all of the numbers in, it's largely just multiplications as you go through, and did you get the answer you wanted or not? Random forest is the other machine learning algorithm we're looking at. It's also largely guessing, but instead of trying to map and mimic the neural nets of the brain, it's basically a decision tree. And what it's doing is it's randomly guessing at what the decisions are until you get an answer that you like. And a random forest is basically throwing a whole ton of decision trees at the problem until they sort of all kind of agree and get you towards the answer that you wanted. In both cases, it's basically just throwing a whole bunch of math and a whole bunch of cases at the problem to get you the answer. I mentioned in machine learning, the biggest part of preparation is getting the data into the format that it can actually do something with. Phase one on that is largely turning everything into numbers. So not everything we look at, and like in the SOASTA data set, we've got things like, these are Samsung devices, this is the user agent string, these are mobile devices. Those aren't numbers. So one of the things that you have to do is turn all of those string things into numbers. And largely everything needs to be a 1 or a 0 or an input in a range between 1 and 0. So what we end up doing is you have a pass that goes through and goes, hey, okay, Apple devices will set this 1 bit here as a histogram, yes or no. Is it a Samsung device, yes or no? You have to be really careful, like UA string in particular is one we left out because we have the UA string problem of explosion. Thank you, Microsoft, and putting every version of .NET in the UA string. So since they turn into a histogram, every different distinct value of one of your strings ends up being a different input. So you end up with 96 or 93 data points ends up being like 10 million different data points if you're not careful. But luckily we have the code that boils user agent strings down into things we care about, platform, device, that kind of stuff, and we take those as inputs so we don't have that same problem. And all of this code is also in the data set. It's more than the 10 lines on the machine learning side of things, but it's not really all that exciting. The other thing you have to do is you want to balance the data. It's really easy to go, and we were talking earlier about another case where you can use like machine learning to do anomaly detection and things like that. In the data set, in the conversion, for example, there was a 3% conversion rate on the overall data set. If we just threw the data as it was at the machine learning, it would be really easy for the machine to go and always guess, no, it didn't convert. And all of a sudden we have a model that's 97% accurate just by always guessing no. So you want to be really careful and watch out for that. And as close as possible, try and get a 50-50 data set on your input so it's really learning what makes the decisions. And so this is another case where you want to make sure you have a lot of data helps. Thank you, SOASTA, for all of the data. When you only have a 3% conversion rate, so you pull out 3% yes, and then you only pull out a random sample of 3% of no, you're looking at 6% of the data now that you're doing the training on. So having lots and lots of data really helps in that kind of case. And then finally, the data needs to be as close to normally distributed as possible for machine learning to do its thing. Luckily, you don't have to know how to do that. There's Python libraries that do it for you as part of scikit, so it's like 2 lines of code. Important here, as you're doing this, we'll talk about this in a second. When we take the training set and we do the fitting, up at the top we have scalar equals standard scalar, so we get a variable that ends up maintaining what the mapping is to convert the data set into a normal distribution. We need to hang on to that for later because when you actually do your feeding of data into the trained model, you need to retransform your data as well to make sure it's on the same distribution and everything. So you want to make sure you store what your transforms are that you did to your data as part of the training. And then finally, it's really easy for machines to learn patterns. You want to hold back some of your data and not give it all of the data and train on that. We usually use 80% of the data to let it train and figure out what the patterns are, and then we take 20% of the data it's never seen before, throw that at it, and see how accurately it detects. And that way you can make sure it's really learning the relationships and not just memorizing the patterns inside of your data set. And finally, at least on the training side of things, you want to be really careful, and it helps to know the data set you're feeding it and the relationships and what all of the metrics really mean in the real world. So when we first started out, we threw all of the fields and we're like, hey, let the machine sort it out. And we ended up in a case where the number one correlation with conversions was SSL used on the session. And well, okay, once we figure it out, it's like, well, duh, checkout pages are SSL. So yeah, SSL is going to be highly correlated with checkouts. So you want to be careful and watch out for giving it inputs that really are more on your outputs than things that you're trying to measure and train against. So we pulled SSL as part of the session out of the data set and fed it all back in. We've removed a couple others as well. So like, yeah, not bouncing. the overall session length was highly correlated with not bouncing. And that's, once you kind of think about it, it's kind of a no-brainer. I'll jump through this really quick because especially in the back of the room, this is probably an eye chart, but it's one line of code to train a random forest. One line of code with 20 different parameters. I'd almost think it was Perl code, but for the most part, you just give it your data set with a bunch of tuning options and you say, okay, go fit and tell me when you're done with the training. And the beautiful thing, and this was, so when we did part 1 back in Santa Clara, we could only get useful, what we really want to know is which ones of these features, which ones of these metrics drive conversions or bounce. And for us, that's kind of the money result is, okay, out of all of these 93 metrics, which ones do we care about? Which ones do we want to look at and focus on? And when we first went back and I talked to the deep learning guys, they're like, oh, well, we told you how to do the deep learning for prediction. You want to learn or understand what it's doing? No. You can't do that with deep learning. So we ended up, the first pass, we ended up relying on random forest, which does let you get some level of importances out. And luckily, it's also just one line of code. Actually, it's not even one line of code. It's a variable that's already stored for you. We did, and training the deep learning, it's 2 lines of code. You have to compile the model and send the data to it. And yeah, so I mentioned deep learning, it's very much a black box. You give it a whole lot of inputs. On your training, it figured out what the relationships are, magic applied. Voila, on the other side, you get your output, your result. We did figure out a way, given enough time, to get it to give us what we wanted, lots of machines and brute force. So what we ended up doing is we took each one of the 93 inputs and we trained 93 models separately with each one of the inputs to see how accurately each one of those came out as a prediction. Once we had, okay, the number one feature that got predicted or drove the most accurate prediction was X, let's try training 92 models with that feature plus every other combination of every other feature. Lather, rinse, repeat, keep going. So you end up training, depending on how many features you need that end up driving what you're looking for, you could end up creating tens of thousands of combinations as you're testing to see what works. Luckily, it ended up, I don't think any of them we needed to go beyond 2 or 3 features combined before it started getting diminishing returns on the training. So luckily, in both cases, we ended up with, hey, these are the 3 features that really are involved in making a decision on whether this session is going to bounce or convert. And then one of the really cool things we could do once we had the deep learning model is we have a trained model that can predict based on 2 or 3 inputs whether a session's going to bounce or convert, and it'll tell you what the probability is that that session's going to bounce or convert. So we could take a synthetic set of data. In this case, I took every 100 millisecond interval from 100 milliseconds to 20 seconds for each one of the inputs that ended up driving. Put that into a prediction model and have it spit out what the probability is for conversion or for bounce for all of the inputs on that range, and you can plot out and see, hey, now we can all of a sudden see what the impact of varying each one of those inputs is on bounce or conversion. I'll let Tammy give you what you actually came here for, which is the resulting data.
So huge caveat before I proceed with this, because I think that we didn't make it clear enough, or I didn't make it clear enough when we presented this in Santa Clara, is that this is what we learned using our massive set of aggregated data from a lot of different retail sites. So just as a for instance, when we presented this a few months ago, one of the things that we talked about was the fact that start render didn't seem to be a meaningful predictor of conversions. And everybody was like, oh my God, what? Start render? But I measure that. That's really important to me. What we find here and everything I'm about to tell you is just what we learned from our data. The whole point of this exercise and the reason why we're kind of like just modeling how we did this is to just show you kind of how it's done, how we learn, how we kind of go back and learn some more and do this in a cyclical way so that you see that this is something that you can do and kind of follow the same process of questioning assumptions, that sort of thing. Our actual findings, you shouldn't kind of take to the bank and say these are metrics that matter to us, because if there's one thing I know from having done a lot of research with a lot of different verticals and a lot of different companies within those verticals is everybody is different. So no unicorn metrics here, sorry.
And that's probably one of the reasons we have the code up on GitHub and not like a pre-trained model for you or anything like that, is run the code or an equivalent of the code on your own data set and see what it means for your business and your metrics. SOASTA has a lot of customers and a whole lot of data, but it's kind of like a smeared vision of things, and your specific case will definitely be different.
So just a little bit about what's in our beacons. So we use MPulse to gather all of our data, and we keep all our data in perpetuity, which is why it's so handy for studies like this. If people ever ask us, why do you keep all your data? This is one good reason. So that if Google comes to you and says, hey, could we use your data for a cool study? You can say, yeah, and do that. As Pat mentioned, we looked at 93 different features that the MPulse beacon collects. The beacon's actually built on Boomerang, and I don't know if Philip is still here. Philip, tell us. There he is at the back, and he's the guy who's responsible for Boomerang and that whole open source project. So this is just a handful of some of the things that we captured. Just kind of putting up there. If you want to learn more about it, you can follow that link, and the entire list will be there.
All the slides will be up on the presentation as well for downloading, so
yeah,
you don't have to write the link.
Yeah, we'll post them this afternoon. They'll be there, and we'll post the link on Twitter. Okay, so what we found, I'll just give you a little teaser. It was really exciting because I know Pat doesn't like to give the same talk over and over again. So I was the kind of one who suggested that we talk here, and we hadn't even done the first talk yet, and I was already trying to get you to commit to the second one. And fortunately for Pat, and I think just for the sake of this kind of research in general, we found enough things that were the same as what we found in our first pass, that we weren't going, oh my God, we're idiots. And we found enough things that were different, but we know why they were different, that it's interesting and relevant, and Pat is here and actually wants to talk about it. And then a couple of new things that weren't there in the first round either, things that we didn't notice in the first round. So when we presented in Santa Clara, one of the things that we talked about was that when we looked at when we looked at all 93 metrics, they all seemed to matter. They all affected conversions in some way, shape, or form. Here, what was really interesting was we found that not necessarily everything was a great predictor of bounce rate. Sorry.
Yep. No, I was just looking at the scale. It's important when you look at sort of some of these scales and data. Remember I said if you guessed no all of the time on a 3% data set, 97% would be just always guessing no. 50% is the baseline of just tossing a coin. So 50% is really the zero level on how accurately any one of these metrics are driving anything. So the fact that you have these really tall green lines, and I think this is probably from when we have two metrics, the baseline's around 70. So the really tall green lines, it's really the top edge of that green line doesn't add any value.
Does that make sense? Okay. So yeah, we kind of highlighted the area. So it's almost a third of the metrics they're relevant for other things. They just weren't great predictors of the two things that we looked at, which are bounce rate and conversions. And the reason we looked at bounce rate and conversions is because they're pretty meaningful metrics for most people. Regardless of what kind of site you have, you probably care about people staying on it. And then obviously for retailers, conversions really matter. So as you can see, the ones that kind of really matter to that tiny little cohort off to the left of conversions. And when we actually look at the first two of those, we found that the ones that were most meaningful in terms of bounce rate were DOM ready, it as DOM content loaded, and average session load time. And Here we saw that combining both of these metrics, so as Pat said before, doing the first pass and then doing the second pass where we looked at DOM ready combined with load time, that got us up to 89.5% accuracy. And maybe, because you sort of mentioned this in Santa Clara, like just what were the percentages where we considered it actually relevant? It was.
I mean, anything over 50 is an improvement. 90% is really good in general.
Yeah.
And to be able to do that with only two metrics was actually, I expected to have the machines running a whole lot longer than we had them running and need to go into like 5 metrics deep to be able to go this high. I was really impressed. And the machine learning guys were very, very happy to see prediction rates in the 90% range.
Yeah, that's what I recall from Santa Clara. Okay. And then the thing that's interesting, I don't know if you can see this at all, but the blue line is DOM ready and the red line is page load as those two metrics. And when you look at them, you see that it kind of just goes up and to the right in a good way. We like that. Where you see at around, let me see, I'm gonna look at this number myself. At around 1 second, that's when you start to hit the climb, and at just around 4.5, 4.8 seconds is where you kind of get into the probability increasing further. So what's meaningful about this is that you see that as page load improves, or sorry, as page load slows down, you see that it has that higher impact on bounce, and so the slower the pages get, the more the more bounce increases.
And it's, I mean, what I found really interesting about this is you really need to be under 4 seconds for the DOM content loaded. I think it was around 6 seconds for the page load time. That's still not good. That's just you're not in the plateau of you've already lost them anyway. And as you get faster, there's no sort of point where you're done. It's almost a straight line down and to the left. The faster you get, the lower your bounce rate. And actually, once you get down below a second or so, any incremental improvement you can make is a even more significant improvement in your bounce rate. Granted, I know there's sort of points of diminishing ability to improve those performance numbers where the engineering effort is maybe not worth the improvement you get. But from a straight, at least from what the machines are telling us on the predictions, this is all the probability of bounce for any one of those times. Pretty much the faster you can go, the faster it's going to get, and it's almost a straight linear relationship.
And the thing that's interesting to me about this particular graph is it kind of maps to other graphs that I've done in sort of similar research where I've used the phrase performance poverty line before, the point at which, like, you know, your conversions get so low or bounce rate gets so high that it just kind of plateaus. So it doesn't matter much if your page takes 6 seconds to render or 15 seconds to render. You're pretty much, I mean, it still matters, obviously. You don't want your pages to render in 20 seconds, please. But you know, you got to get, it's when you get below that like 5 or 6 second mark where you can really see greater returns on your investment in performance. So this was really interesting too. We found that when it came to getting high predictability, so we had almost 90% on the bounce data, it was a lot tougher to get high predictability on the conversion data. And so with this set of numbers, we actually had to make 3 passes and connect 3 different metrics to get something that added up to something meaningful. And here you can see sort of the same idea. Things get meaningful at kind of the top of the red bar. And we got as high as 81% prediction accuracy, which is still good, but not as awesome as the 90%. You were less enthused about this one.
I mean, that's why I'm more excited about the bounce data.
Yeah.
Both because it's all about performance and because it's really highly predictive. And bounce pretty much applies to every industry, and it's really easy. If you're a publisher, bounce makes a whole lot of sense. If you're e-commerce, bounce also makes a whole lot of sense. So
I'm not surprised that this was a little bit harder to call, because one of the things that's challenging on the retail RUM side of things is even just like it's all apples and oranges, right? Like this retailer's conversion rate is very different from that retailer's conversion rate, and even how they define conversions. So it's tougher to measure, and anybody who works in retail who's in this room will probably say the same thing. So 81% was pretty good, and I will go into which metrics were specifically. There's really just one that dominated, and that was finding number 4, pages with more scripts were less likely to convert. So if you're in Santa Clara, when we did the first pass over the data, we found that pages with more scripts were more likely to convert. But then with the filtering that we did, where we filtered out basically some of the things that I think, correct me if I'm wrong on this, the machine learning had kind of learned about the wrong.
So when we were looking at the random forest, we didn't really have more or less. So we were just we couldn't plot out the prediction rate. So we were just kind of going, oh, okay, more scripts. We didn't have the data to tell us which way and which direction it mattered.
Yeah. So what this looks like, it's really interesting. So you see that this is the x-axis here is all of the number of scripts. I don't know if you can read this in the back. And
the fact that it goes into 3 digits should probably scare the crap out of you,
yes.
Just in general.
Yeah, and like, a not insignificant number of them do.
Yeah, I mean, it goes up into 4 digits at the end there, so.
Mm-hmm. So
these are script tags, not necessarily external scripts, but that's still a whole lot of script tags on pages.
Yep. And so you can see that like before, around 300 scripts, it's possible that the machine learning learned some of the patterns of what checkout flows look like. That was what you said in terms of explaining the randomness. But after around 300, it evens out and gets into a pretty nice predictive model where you can see that, as more and more scripts are on the page, that it hurts conversion.
So, I mean, this one for me, it's basically, as long as you don't go nuts with your scripts, it's fine. But if you've got more than 400, 500, 600 scripts on your page, yeah.
Don't be on the right half of this graph if you can help it. The other thing we found was that the number of DOM elements matters a lot, and here's what that looks like. So you can see that kind of your sweet spot is like between 400 and 700. Then it sort of plateaus out, and then after 1,000, but really after about, what's that number? 20, like around 2,300. Yeah. It just kind of plummets. So that's kind of the painful area right there. So yeah, we're looking at pages with like 9,700 or I guess close to 10,000 different DOM elements. So same idea. You don't want to be on the right half of that graph, or really anywhere in this red zone if you can help it.
So both of them, it's basically try and keep complexity sane.
Yeah.
I mean, it's not even like minimize it. Once you get up into some of these numbers, you've gone off of a deep end anyway.
The other thing that was consistent with what we found in the first pass was that mobile-related measurements, those metrics weren't really meaningful predictors of conversions. So this is really interesting to me. We looked at, for example, this is all 93 different page metrics. So we look at median bandwidth is kind of around the middle. Device type and mobile connection type are down there at the bottom. This is for bounce. I could show you a very similar one for conversions. It was the same thing. They were actually even all a little bit lower down. Like median bandwidth was even lower down on the list. And I guess the takeaway there, we talked about this a little bit a few months ago, was that it's not like mobile web anymore. It's just web. People expect experiences to be speedy. People bounce at pretty much the same rate, regardless of whether they're on desktop or mobile. You can't really kind of segregate out user behavior and think that, okay, people behave this way on desktop and this way on mobile. They just behave the way they behave across the board. And then this was kind of the biggie, because this sort of freaked some people out. Because somebody had a talk before us in Santa Clara where we said that start render was 69th out of 93. But actually, when we went back into the data and filtered some things out, kind of realized that the issue there was that our beacon gathers start render data, but it's not supported by all browsers. So when we filtered out the browsers that didn't support it and just looked at that data, it was something like about 280,000.
Yeah, I mean, it was
out of a million.
If you look, Safari and Firefox, neither one does any start render. So if half of your browsers aren't supporting the metric, it's not useful largely as a predictor.
Yeah.
And so this is sort of another case where it really helps to dig into the data, know the data, and also know what all of the metrics are. You don't want to just kind of blindly throw it over to an analytics team and say, okay, go figure stuff out with this data. It really helps to, and when you see something like this, I mean, start render not being important just floored me. When we were at Santa Clara, I was like, okay, I'm just quitting this industry, I'm going home. All the work I've done on web page test around visual metrics, it's like, no. So yeah, and that's probably what drove me into actually digging into each one of the records and looking at the data and seeing why. So when you get something that ends up being counterintuitive, definitely dig into it and see if you can figure out why. It's not unusual for your source data to not be quite as clean as you would hope, especially in a RUM situation where you've got stuff coming in from the field. You get all sorts of crazy things in there.
But you raised a really good point. Like, this is the value of having like a cross-disciplinary team, right? Like, you need people who understand the metrics that you're capturing. You need people who understand the business metrics as well. So, and you need people who understand like how the browsers work. You know, so it's like you have to have people coming into it with their own areas of expertise and actually like speaking to each other so that you can filter these things out. And then, yeah, as Pat said, if you see weird things, you need to be able to go and dig in and find out, okay, why is that weird? So we actually found that start render was like shot right up to the top of the list.
Well, close to the top. I mean, it's important to note that DOM content loaded still ended up being a more important driver than start render, even when we had both in the same data set, which is good since DOM content loaded is available on all browsers. But if you think about it, it's not terribly surprising because it tends to include a little more of the user experience. It'll also include when the browser becomes more interactive. You've generally hooked up most of your JS to the UI and things like that. So DOM content loaded being more of a predictor than start render, it's just because it's a little more of an inclusive metric about the user experience.
Yeah.
So it helps that it actually makes sense and I can rationalize what came out of the model.
This reflects my worldview.
I feel good.
All right, so I'm going to pass it over to you. Pat's going to...
So I mean, we talked a little bit about like SSL correlated and why we had to pull some of the things out. Sort of one of the other things when we were training the deep model is you also kind of want to watch out for, is it just sort of learning the patterns? And like in the conversion, and this is sort of one of those reasons I'm also not as excited about the conversion as the bounce. It's like, hey, the maximum server response time ended up being like the #1 predictor in conversion, and it's like, okay, yeah, it's basically just telling us that checkout flows are slow, and the slowest step in almost any flow like that is going to be the credit card validation. So one of the things that you can do, and we just haven't had a chance to do this yet to mitigate some of this, I wanted to take a look at a data set where it's just look at the initial landing page the users came in, so you have kind of a clean read on the data set, and did this session end up in a conversion? It won't necessarily give you as much value about looking at the whole pipeline, but at least you can have a clean read where the checkout pages aren't included in your training set. So maybe there will be a part 3, we'll see. The other thing, and this, especially when you're doing like the brute force machine learning, iterating, when the first metric that came out was the median DOM ready time or DOM content loaded time. On the second pass, the top metric was for predicting bounce or not, was max DOM ready time. And that's pretty easy once you think about it to figure out that, hey, if the median and the max are different, there were 2 page views, it didn't bounce. So you have to sort of mentally look at and make sure all of the metrics make sense. In the case when we were doing this, I'd do any future pass that included previous metrics would not include a metric that was related to one of the earlier metrics. So in the second pass, anything that was DOM content ready or DOM content loaded would just get X'd out and wouldn't count, and we could look at the other metrics. But so watch out for the relationships between the individual metrics and the machine just learning what that relationship is rather than the actual behavior. I think back to Tammy.
All right.
Tag.
So, I think we sort of covered this earlier, like, use your own data, do this at home. I guess the question that somebody asked me earlier today when I was talking about this a little bit, I never really thought to answer because it seemed really obvious to me. It was like, well, why? Like, why would I do this other than, well, you have a lot of data, it's there. Like Everest, you just climb it because it's there. The two big reasons why you can do this, and we talked about this earlier, Pat, was one is so that you can actually figure out if you've got this beacon data and you're gathering data around all these metrics, what are the metrics that you can actually get people in your team to care about, like so that everybody's kind of like running towards the same finish line. And then two, the predictive aspect is, okay, well, we know this about that we're heading towards the finish line for these two metrics, but what difference will it make? And so the predictive aspect is, because it's not correlative, it's predictive, we'll tell you, well, if we make our pages 1 second faster, or 500 milliseconds faster, or whatever, we'll probably see this return in terms of bounce rate and conversion. So it's just to kind of give you some certainty in your team about what you want to do.
And for setting the goals. If
yeah,
you want
exactly.
to pick, okay, we want to improve the bounce rate by 50%, okay, where do we need to move our performance needle to get there? Mm-hmm.
And then, get your own data. You should have, if you're collecting RUM data and you don't know what to do with it. Somebody made the point yesterday that like people are sitting on all their data, they only use 5% of it. This is how you can use that other 95% of your data. And Pat's giving you the code to do it. And then if you get unexpected results, as we did, keep digging. Ask different questions, run different filters. Make sure that you understand all the different metrics, and you have this 360 view of every single variable that you're looking at, and just keep asking questions.
Yeah, and even you don't have to like write your own and collect your own RUM. If you're using analytics, Mpulse, just about any of them, we'll provide a way for you to get the reporting data, to get your raw data, to be able to do this kind of thing on it.
Exactly. So thanks. And please go online and rate this talk. We would really like to get your feedback. Thanks. So we've got a couple of minutes for questions, but there's a break after this, right, Steve? So if people have more questions, we can hang around a little bit. Great.
Okay. Jim.
A lot of metrics if you work back. You can have a lot of scripts if you work back.
So did we look at the correlation between the metrics themselves? Not a whole lot, although I will say the charts we showed were somewhat simplified. We had the DOM content loaded as one line, and we had the page load time as a separate line. Those are if we looked at those independently. When you end up with the deep model, and to get to the 90%, we actually had 2 inputs. So it's a single model with 2 inputs, not 2 models with 1 input. And we then actually end up with a 2D plot or a 3D plot of both variables at the same time because they will interact with each other. I didn't have time to do, and I don't think it would actually graph that well on the projector, but if you're really doing it, you really want to have and go, okay, we need to lower DOM content loaded by 3 seconds and page load time by 2 seconds to get to whatever this bounce rate. It's really the combination of both of those. We didn't look at the correlation between every one of the metrics, though. Have we applied this to Google search page? Not explicitly. The search team already has a lot of metrics, and I think we've already talked about at previous velocities about every 100 milliseconds improving by X% on searches. Largely, they don't need to be convinced to improve performance. They track it like you would not believe, and they watch the business metrics as it improves. Their goals are faster, always faster. They don't actually have an explicit target. I will say we'll probably look at doing this. I know DoubleClick did a study. They haven't run the machine learning on it yet, They did a study with analytics that they published a few days ago, maybe, that had largely similar correlations. They had analysts, data scientists look at using analytic techniques. We'll hopefully be able to do similar things with the machine learning and get stuff out of there as well. But no, haven't run it on the Google search data itself.
We've actually, this isn't a question that you asked, but I just should do a little plug about the fact that we've actually, we're working on machine learning at SOASTA, so actually making that, there's a whole data analytics layer that sits above mPulse. So that's something that we're actually actively working on, and there are elements of it in our latest release, which just went live this week.
I should say, anything we learned on Google search would probably be useless for everyone else. Not the least of which is Google search's entire goal is to bounce as quickly as possible, which is kind of the opposite of what everyone else on the planet wants. Is this all retail industry? Well, it's a combination of retail and publishers, right? It was a sampling of all of your data.
Yeah. So
heavily skewed towards retail.
Yeah, a lot of our customers are retail customers.
Did we look at subsets? We threw all of the data at it. We did have like the vertical and that kind of things were separate inputs. Ended up not being something that the machines picked out as being important, but we didn't explicitly carve down and look at individual retailers or subsets like that.
No.
Yeah, so the point or question was that if you're looking at conversions on retailers, even if the performance is horrible, if it's an incredible deal, the conversions are still going to be really high. And yeah, I mean, all of that, there's probably a lot of business things around the user really needed socks, so they bought socks, or they didn't need socks. So the conversion stuff is definitely not. And that's sort of one of the reasons I like the bounce stuff better, is it's easier to rationalize how much they're using your site, whereas you can't necessarily go to Amazon and say, hey, increase all your prices. As long as you're fast, they're going to convert, right? There's a whole lot of other things that drive conversion.
But I think this is the value of just throwing a lot of data, as opposed, because there's always going to be use cases like that, right, where people are going to come to the site because you are the only retailer that sells that product, or you've got some amazing flash sale or something like that. But if you have enough data over time, then you can find these patterns that are kind of sort of supersede that kind of use case.
And I mean, if you run this on your own data set, and you can say, okay, let's look at the performance of all my flash deal sites or pages, and then see what impact did the performance that any individual user have on their ability to actually go through the flow, or if they had 5 minutes on the train that they were just kind of browsing around buying stuff and seeing, if they have a limited time window to do things, did any of that drive the conversions or not?
But I can't say, so we have a lot of retail customers at SOASTA, and I won't name any names, but there are customers that have had flash sales or campaigns directed people towards landing pages, and they realized that there were performance issues, and it didn't matter how great the sale was, people still bounced, people still didn't convert as much as they wanted them to. So that's a factor, but performance still matters even in those situations.
The split on the data, desktop versus mobile, was it US focused? So it wasn't, we had an even mix of mobile and desktop data in the data set. We didn't actually split it when we did any training. We just had, is it mobile or desktop as a metric or flag. As far as, I think the data set is skewed towards the US. There are some non-US retailers and things, and there's definitely non-US traffic, even though they're largely US customers. But here, and then we'll go. Well, you should probably dig into the data even when you get results you expect, and that way you can be scientific about it. But that one drove me particularly nuts, which is why I spent the extra time looking into it. But I looked at a whole bunch of things even when we did get to the results we kind of thought we'd see. I'd say review the metrics, but also just kind of look at the raw data, sample through the data, and see that the data, I looked at, okay, what's the distribution of the data? What's the range on the data inputs? Do I expect that to be the right distribution for these metrics? Does it look like the device type is missing on half of the pages, for example, or something like that? Just kind of do a sanity check while looking at the actual data itself to make sure you really got what you expected and you're running. Back and back. Can I ballpark the approximate number of person hours that were spent on this effort? More than I would have liked, because I was also figuring out how to do the machine learning.
That's the thing, right? The curve is pretty steep at the beginning.
Yeah, I mean,
for all of us.
It's certainly in the hundreds of man hours, but not thousands. It was just me and a few other guys who actually knew what they were doing got me started, and then it was me just kind of make a few changes, run the models. Running the models, you just let the machines run for a few hours, so I won't count that as man hours. I wasn't actually watching them. Well, I was watching them because I kind of liked watching the numbers and go, okay, how is it improving? But probably on the order of 100 or 200 man hours total. Simon. Any chance on releasing the anonymized source data? Unlikely.
Probably not, no.
Sorry. But you have your own data for your own sites. So certainly if you rerun some of this kind of stuff on your own data, publish, talk about it, let us know. It'd be nice to get sort of contrary opinions or validation that, yes, I found that it held true with our data. And especially if you run it, target an improvement, make the improvement, and see the result. Did the result match the prediction?
So, yeah, at SOASTA, we're really lucky in that we have so many customers who have contractually agreed to let us do this kind of research on their data as long as it's anonymized. I can't thank them personally, obviously, because that kind of like ruins the point of it. But they're really great, and I'm very grateful to them. And if you are one of them sitting out there, then thank you very much.
Yep. All right. Okay, thanks. Cool. Enjoy your break.
Yeah. Thank you very much, everyone.